Hello. Yep. Let's get started. Um, yeah. So we are for the next 3 lectures sort of entering the next step in our journey about lossless compression, going beyond IID data. Okay. So we started the course. We talked about very simple prefix codes. We talked about entropy, and then we started. Then we looked at AEP, which provides like a theoretical foundation for compression. And now, like after that, like the last 3-4 lectures, we have been talking about specific entropy coders. So let's take a quick tour of those. We talked about Huffman coding. It's very fast. It is the optimal coder when you're doing like a single symbol or you're doing a particular block. And it will achieve entropy when you work with larger blocks. Of course, the complexity increases exponentially. So it's great in many settings, but you run into this complexity limit when you want to really get close to entropy. So that was the first coder we saw. Actually, any questions about the project before we move? Yep. Okay. Then we saw arithmetic coding. This was a different style of algorithm where the entire input was a single block, and we saw that it will achieve entropy efficiently, basically linear time instead of exponential time, as in the case of Huffman coding, and it reads the entire input as a block, getting a very small like 2 over n overhead over entropy. So it's great. One main issue is that it involves certain division operations. When you actually do arithmetic coding, like if you do it in float domain, you need like floating point multiplications, which are expensive. If you do it as an integer, which is the more common way, you need division operations, which are again expensive. So it is good, but you won't see arithmetic coding being used in like fast compressors. It's still used in a lot of heavy duty type compressors, and we'll look at some examples. One nice property of arithmetic coding, which will be important to us today and next lecture, is that it works with very complex probability models, far beyond anything we have seen until now in this class. And we'll see some examples next lecture. Okay, finally we looked at ANS in the last lecture. There are 2 variants, RANS, TANS. We mostly talked about RANS, but both of them have their own strengths. Again, they achieve entropy efficiently by treating the entire input as a block. TANS doesn't quite achieve entropy, but it gets close. There is a small overhead over arithmetic, so it's not the best compression, but close enough. Both of them are faster than arithmetic coding, with TANS being particularly fast. It almost approaches Huffman coding speeds. And finally, like the algorithm we see in class is always very simplistic, right? It's like a Python pseudocode. People have figured out how to implement ANS in extremely efficient ways on modern CPU architectures. And that is sort of the reason why it's becoming more and more popular today. So there is only so much we can cover in class, but here are some links if you are more interested in these topics about these entropy coders. The paper by Jarek Duda on RANS and TANS. A few blog posts by people who have actually implemented these algorithms. And really like a lot of sort of the good stuff in compression is on this Russian forum for some reason. But all the big people like Jan Kollett, the creator of Z Standard, and Jarek Duda, the creator of ANS, all of them are on that forum, and they comment on all the latest developments on compression. So if you're interested. Okay, and then this is a table we have been seeing a few times in the last few lectures, right? So Huffman coding 1950s, then 1970s, and then very recent ANS. And they have different speed profiles, different compression ratios, and so on, right? So Huffman coding is the fastest but worse compression, right? RANS, arithmetic coding is the slower one, but best compression basically for the complexity. And RANS and TANS are faster than arithmetic coding and better than Huffman coding, so somewhere in the middle. One thing you note here is that RANS has a very fast decoding compared to arithmetic coding. And we'll look at that in a minute. In many applications, decoding time is crucial, and RANS wins out on that quite a bit, and TANS even more. Okay, so last point on these is that all of these entropy coders are used in practice, sometimes because they are the best tool for the job, and many times because people have been using it and it's hard to switch compression formats, so just legacy reasons. But they have their unique properties, and we will keep coming back to these both in the next few lectures and in lossy compression. Okay, any questions on this sort of whirlwind tour of entropy coders? Right. The main sort of thing we are doing with this entropy coders is start with a probability distribution, known probability distribution. You have data drawn according to that IID probability distribution, and you want to compress it to its entropy. Basically, that's the block diagram vision of this, right? So you have known P, which is IID, and you have like x1 to xn, and you take your entropy coder, and you get like bits, and you want like this number of bits to be roughly equal to n times the entropy of x. Right. So this is sort of all of these entropy coders fit this basic block diagram. Okay, moving on to the quiz, which hopefully we can do very quickly because I wrote down the answers. Okay, so the first two questions were about RNS encoding and decoding. You just needed to follow the formulas as you saw in class, right? So we have some encoding step, we have some decoding step, right? Quick thing I want to note is that see, in the encoding you need to divide by the frequency of the symbol, and divisions are bad. Basically, that's like good to know. Whereas during encoding, you see there is only one division step, but it's division by m, which is usually a power of 2. So division by power of 2 is very, very cheap on a computer because you just shift left by or shift right by something. So that is like the main reason why the decoding is so much faster, right? If we saw in a couple slides ago, the decoding for RNS was almost double the speed of the encoding because the decoding doesn't have this division operation that the encoding has. So we have this formula. Let's just do it. I won't spend too much time. Talk to us later if you didn't get these. Okay. So you are given some alphabet 0, 1, 2, and you have your symbols with these probabilities 3 by 8, 3 by 8, 2 by 8, right? So first thing you would do is you will say that the common denominator of all these is 8. So you will set this capital M equal to 8. And then you will make this table, which is like symbols, their frequencies, so 3, 3, 2, and the cumulative, which is the running sum of these guys, right? And then you would just apply the formula, right? So let me do one of these. So initially the state is 0. So you do like 0 divided by frequency of 2, which is 2, multiply by 8, plus the cumulative of 2, which is 6, plus 0 modulo frequency of 2, so which is 6, right? Anybody had any issues with this question? Let me know, otherwise I will just write the answers for now. Right. You're just supposed to follow this formula, just do the computations. Okay. Right. Let me do the next one. So 6 divided by frequency of 0 is 3, multiplied by 8 again, plus cumulative of 0, which is 0, plus 6 modulo the frequency of 0, so 3. So 6 modulo 3 is 0. So only the first term survives and you get 16. After you do all of it, you should get 114. Right. Just substitute. Okay. Second one, we asked you to decode. So you were given something where the final state was 117 and you had 4 symbols and you are supposed to now decode it. Again, make the table, right? Yeah. Make the table. And what do we have here? We have, we will follow the steps which you can see. Yes. Okay. So let's do this. So block ID is 117 divided by M, which is 8, and you take the floor, which if you do it is 14. So block ID will be 14. Slot is 117 modulo 8. So 112 is a multiple of 8. So this will be 5. Then this step, find bin cumularray slot. So what this means is you make this sort of thing where you mark the different symbols, right? So the frequency of 0 is 3. So this is 3. Then frequency of 1 is 3. So 3. Frequency of 2 is 2. Okay. And then you need to locate 5 in this thing. So because your slot is 5, so 5 is here, right? So this slot was 5, and then S is equal to 1 because this lies in this slot. And then you do this calculation, block ID times frequency plus slot minus cumulative S. So block ID was 14 times frequency of 1, which is 3, plus slot 5 minus cumulative of 1, 3. $44. Okay. Right. Any questions? So one quick thing is like, again, like always focus on the main step, right? So main thing here is this step really. So you are doing, what this is doing really is, X next is X multiplied by, or yeah, so you're doing X divided by the probability of X really, and all of this is like doing X multiplied by probability of X, right? So that is the main operation. That is what gives you the log 1 by px result and so on, right? So just remember that is the core lesson. Please watch the lecture from last time or do the last question in the homework if you want to learn more about RANS. Okay, here I will ask for your help. So the question is like, when do you want to use ANS as opposed to Huffman or arithmetic, right? So first part, your application requires the best compression ratio and you are willing to sacrifice encoding or decoding speeds. So what do you think should be the answer here? Is ANS the best answer or something else? Okay, I see some heads shaking. So here actually arithmetic is typically the best answer. Talk to us later if you thought differently. Your application requires extremely fast encoding, decoding, and you are willing to sacrifice. So here the answer is clear, it's Huffman, right? If you look at that table from a few slides ago, you can't beat Huffman at speed. Okay, just so simple. Your application requires adaptive decoding. So we haven't talked as much about this adaptive stuff yet. I think we mentioned it in class. We will talk about it next lecture. Again, talk to us if you were confused. But here really the best answer is arithmetic coding. I think this was in one of the slides last lecture. Okay. But you will understand what we mean by adaptive in the next lecture. Okay. Okay, so the last two, you care about achieving close to optimal compression but also want good speed. Here, I hope some of you thought ANS was the answer, and yes, indeed it is. And the last one is, you are working with a modern processor, want to exploit parallel processing while still achieving close to optimal compression. So this is this SIMD stuff that I was talking about, single instruction, multiple data. These are special instructions on the modern x86, like the Intel machines, also similar on the ARM machines, where if you're doing the same sort of operation again and again, you can parallelize that operation. And it's very interesting the way they do it with RANS. I will not talk about it too much, but the basic idea is like you have your symbols, right? Symbol 1, symbol 2, symbol so on. What you do is you compress symbol 1, 3, 5, 7 and symbol 2, 4, 6, 8 in parallel basically. Which is like very, very suitable for these modern processors who can do these two operations in parallel basically you get 2x speed up without using 2 cores. You need to write the code in a proper way, but I think there was a paper I linked in the, if you want to read more, this paper. So this paper should give you a sense of that sort of parallel encoding decoding. Okay, so here the last two are the answers. Sometimes these are a bit confusing. The idea is to like get you to appreciate sort of the relative importance, like relative strengths and weaknesses of all these compressors. So yeah, in this case, the last two. Okay. Okay, any questions so far? We'll now start the material. Yeah.
Just a quick question about the first choice. I actually thought that one was true because if you look at like the table of the speeds, like T and S actually has like the same like optimal compression ratio and like significantly higher like encoding and decoding speeds compared to arithmetic. Like that's it.
Yes, so if you look at these two,
Like, no, but compared to like T and S.
yeah, but even RANS, right? RANS is same compression as arithmetic in this table, and it's just faster at decoding. TANS is slightly overhead, I guess. It depends on the use case. Talk to us. Yeah, talk to us, or make a regrade thing, and we will consider. I think the first one, I agree, might be a bit. It's not like as clear. Yeah. Okay, honest advice. If you have IID data and you know it's IID, don't use arithmetic coding. Use RANS or TANS. Simple, right? You don't want to use arithmetic coding for IID data. Really today, the only reason to use arithmetic coding if you have non-IID or adaptive type of data distributions.
Can I start another point? So that table is on a specific data, right? So don't overread the table. That is going to like motivate us not for everything out there. As Shubham has been saying, and as with the next few lectures, the real use case of arithmetic is that it allows you to adaptively work with probabilities, which is sort of the best thing which you can do, no matter what, because of the reasons that we'll learn shortly.
Yeah. But make a regret thing. I think let's not worry too much about. These are like small things. I think as long as you understand the concept, that's what matters. Okay. We will move on. Yeah, but you will see arithmetic coding is much more powerful. We haven't seen like the full power yet. Okay, how many of you have seen this, read this novel, or identify the novel? Anyone? Disappointed. Okay, so this is the Hound of Baskerville by Arthur Conan Doyle, Sherlock Holmes, right? So it's a nice book. This is like one of the paragraphs. Okay, so we read all these entropy coding and so on, right? So I thought let's try to compress this book, right? And I basically called this get entropy function to get like the entropy, the empirical entropy, right? You compute the frequency of each of the letters and you do it. And I got this 199 bytes, 199 kilobytes, where the original file was 387 kilobytes. So that's good. That's roughly a 2x compression. We are happy? No, we are not, because then I tried to compress it with gzip and bzip too, which are some standard compressors. They're not even state of the art. They're like pretty old, 20-year-old compressors, 30-year-old now, right? And they get much smaller than entropy, right? But didn't we study that entropy is the best you can do? Entropy is the lower bound on any prefix-free, any lossless compressor. Okay. So, any suggestions? Why is entropy not the best you can do? Actually, some of you might have noticed it in homework 1. I think we had a question where we asked you to do gzip on a file and you saw that it was better than Huffman.
I think it has to do with the fact that like each letter, like you can look at the probability given the previous letter. For example, like if you have the letter T, like there's a high probability next that's going to be like H, for example. Like so maybe like with that you can get like better performance. Like.
Yeah. Yeah. So the very, very good answer, which is that all of this is based on IID assumption, right? For the first 7 lectures, we just studied IID. So there is a risk that we assume the world is just IID, everything is independent of everything else. It is not, we know that. So the example was, if your previous letter is a T, you know with very high probability or with some probability that the next letter might be a T, H, right? You have the, then, this, that, like a lot of words like that. Even stronger example, right? If your previous letter was a Q, you know with even higher probability that the next letter is going to be a U, right? So, or if you're like doing English, right, and you had a start of a sentence, you know that the first letter will be capitalized, and then you have like small letters. You know that. So there are a lot of things you know about English, which are not explained by this IID property. IID would just say that you have 15% E's and 10% T's and so on, right? But it says nothing about like if the previous symbol was something, what is the next symbol? So again, IID means independent and identically distributed, right? So which says that each of your symbols is independent of each other, and they have the same distribution. But what you will see is that given your past, actually the distribution keeps changing from symbol to symbol. So that's the first thing. And there are other reasons, right? Like if you just compute the entropy on you just concatenate 2 files. You take Java code and you take the Sherlock Holmes book and you concatenate them. And you compute the entropy on both of them. The entropy will be like a mix of the 2 entropies. It's not the optimal thing to do for either the Java code or for the Sherlock Holmes file. So for these 2 reasons, but really the first one is what we'll focus on for now. Okay, so we'll look at non-IID data, right? We'll look at real life data now. So we'll look at real life data. We will do 2 things. One is non-IID data, and the other is data whose distribution we don't know a priori. So in homework 1, you already saw an example where you were given a file and you computed the empirical entropy, you encoded it with Huffman coding, you stored the code book, right? So that is one way to do it. There are other ways we will look at where, right, like it's easy to say that I get like 50% zeros and 25% ones and 25% twos, but who has seen a real distribution like that, right? Oftentimes when you start with a data source, it's very complicated and you don't know the distribution often. So, right. And we have been talking just about text, but think of images, right? Like if I'm compressing this image, this slide, right? Like it's very correlated, like the nearby pixels. If the nearby pixel is white, it's more likely to be white. The black guys are all like bunched up together, the black pixels, right? If you have a more like scenery sort of thing, you have sky, the blue colors are like nearby. So there is some correlation nearby, right? If you think of video is also, right, like nearby frames, right? Like even if there is motion, there is a slow motion. So nearby frames look very similar. So again, there is some dependence. Tables and anything in real life, everything is non-IID. Nothing, like very rarely do you get like from nature or from real life a thing that's IID. Okay. Any questions on the motivation part? Right. So, quick outline. Today we will look at for some of you who have done a lot of probability or information theory, today's lecture will be a bit redundant. So please bear with me. Next lecture will be new. Also, if you don't like theory, today's lecture will have a little bit of theory. So again, please. Then lecture 9. So today we will do like basically the equivalent of entropy, but for non-IID distributions. And then we will do next lecture. We will start looking at some more like some practical schemes. For lecture 9 and lecture 10 are mostly about like schemes for achieving the optimal for non-IID data. And really lecture 10 will be like the last lecture of lossless compression, where we will summarize everything we have learned and look at a bunch of case studies, see how to apply lossless compression in practice. One thing is, I guess I said everything is non-IID, but like don't get disheartened. It's not like everything you have done is useless, right? We will see that all of these tools we have learned are very, very useful in the this case also, right? Also for lossy compression. Okay. How many of you have seen Markov chains in a previous probability course or information theory or any course at all? Okay, a few of you have, some haven't. It's fine. Don't need to know too many properties, but we will need some basics. Okay, which I will cover. Okay. So recall that if you have a block like U1 through UN, in the IID case, the probability of the joint probability of all of these guys is the product of the probabilities. Okay. But in general, if you have done chain rule, you know that you can't just like write it as a product. You need to do this chain rule where it's like PU1 comma U2 is like PU1 multiplied by PU2 given U1, right? That sort of thing. And then you can keep extending this, right? So just the chain rule. If you've forgotten this part of your probability, we can share some material. Okay. So we will just go all in infinite length sequences now. So given some alphabet U, binary maybe or something else, alphabet maybe like English alphabet, you can create a stochastic process. So a stochastic process or a random process is just any sequence of random variables with arbitrary dependence. And it is characterized by basically for every n, you have to describe the probability distribution for that n tuple. Right? So in the IID case, this is very simple. In the IID case, for any n, this thing factorizes. So you write the probability of U1 through UN is just the product of U1, U2, U3, UN, right? But in general, if you don't assume IID, these could have arbitrary distributions. You have just a bunch of like big distribution tables sitting with you. And this is very, very general. And we won't talk about these. You need to, this is way too general to be of much use in theory. But you need to know there is a notion of a random process where it's just a sequence of random variables with arbitrary dependence amongst. Like a random variable might depend on something that's like million before it. Anything can happen. Okay. I will pause for questions after a couple of these. Okay. Then we have stationary stochastic process or a stationary process, which is a stochastic or a random process that is time invariant. So what it means is that whether you are at position 0 in the process or you are at position 100 or position 1000 or million, the probabilities don't change. It's in a stationary state in a way. We'll look at some examples, but if you like define it very precisely, what it says is that for any n and for any L, the probability that U1 through UN is equal to something is the same as the probability that UL plus 1 to UL plus 1 is equal to something. So this is just saying that if you shift your, like, just as an example, right? Like basically we are saying P U1, U2 will have the same distribution as P U100 and U101. So same distribution. Okay, so this is an example of like a stationary process must satisfy this sort of thing where wherever you are in your time series, it will have the same distribution there, same joint distribution. And in particular, like the general definition is fine, but in particular specific properties are that the mean, variance, entropy, all of these do not change with n, right? So what we are saying is like the expectation of U1 will be the same as expectation of U100, for example, or the entropy of U1 will be the same as entropy of U100, or the entropy of U1 comma U3 will be the same as the entropy of U1000 and U1002. So this sort of properties, right? And even these stationary distributions are not like necessarily very simple. They can have arbitrarily time dependence. So in particular, like U1 and U1 billion can be dependent. It's not like they have to be independent. you can have like very far-reaching dependence. Okay, we will keep moving on. We'll look at examples. You never really need to deal with like a fully general stationary process. So we'll get more and more specific as time goes on. Okay. Any questions so far? Okay. So let's say you have IID sequence, which is a sequence of fair IID coin tosses, right? So probability of head is equal to probability of tail is equal to 1/2. Can someone tell me what is this thing? The probability that the first 4 tosses are in sequence HTTH. Yeah, I'm meaning 1/2 which is correct, right? Because this is IID, right? So this is just like PU1 equal to H multiplied by PU2 equal to T dot dot, right? Can somebody tell if I put like some L here? So I just shift it. I'm looking farther in the future, maybe P 100 and 100 and 200 and 300 and 4. What is the probability now? It's the same, right? Because again, it's IID, right? And IID means independent and identically distributed. So all of these have the same distribution. They're all independent. Okay. So you can show with some work that IID implies stationary, right? So any IID process, all the processes you have seen so far are all stationary because they are IID. IID is like a very special case of stationary. Now we'll look at a more complex thing, a Markov process. Right. So a Markov process, if you have not seen one, is you can define it in terms of sort of one-step probabilities. So if you know U1, you can define the probability distribution for U2 conditioned on U1, right? And then if you have U3, then you can define U3 given U2. So the real like property here is that UN is independent of UN minus 2 to U1 given UN minus 1. So what this says is that if you know the just previous symbol, if you know UN minus 1, then your future and past are independent. So the only dependence is like at one symbol level, right? So if you know the previous symbol, that's all you need to know. I tell you like the last million symbols, that doesn't matter. Only need to know the last symbol. That is the property of a Markov process. And I think it's easiest explained through this diagram. So we start with U1, which is uniformly drawn from 0, 1, 2. So let's say you sample 0. Let's say U1 is 0. Okay. So once you are at 0, these arrows show like what is the next symbol. So if you are 0, you see an arrow with 0.5 probability going to 1. And you see an arrow with 0.5 probability staying at 0. So that means that if U1 is 0, then U2 can either be 0 or it can be 1 with half of probability. Right? So it's like a one-step process. I wrote it in another way. Maybe this will be easier for some to understand. U1 is again sampled uniformly and Ui plus 1. So the next one is Ui plus Zi mod 3, where Zi is like 0/1. So basically we are saying if you are at 0, you can go to 0 or you can go to 1. If you are at 1, you can go to 1 or you can go to 2. If you are at 2, you can go to 2 or you can go to 0. So mod 3, right? So you round back to this. So this is saying, this is a very simple Markov process where at every step you either go to yourself or you go to 1 plus u, right? And there are various ways to represent it. Don't really need to like worry too much, but maybe you have seen one of these, not the other. So that's why I made all 3. So this just shows this thing as a table where if you are at 0, then the next guy can be 0 or 1 with 0.5 probability. If you are at 1, then the next guy can be like this too. So that's sort of like another representation. It's called a transition matrix. Or you can write it in the form of an equation, which is not always possible. Or you can write it in this graphical manner. We'll mostly make this graphical manner for the rest of the lecture. Okay, so now let me do this math and stop me whenever you don't like it. Can somebody tell me what this rule is called, this step that I just performed? Okay, so this is just called marginalization, like the opposite of this step, right? Where if you add up u1 over all its values, and then you're just left with u2 basically. So that's marginalization. We will have a quiz question, so I hope this example will help you like do that very easily. Okay, now let's do it this way. P u2 equal to 0. This is very simple. Apologies if you already know this, but we'll do it. Okay, can somebody tell what I did in the second step? This is just the chain rule. Right. These are not hard questions. Just want to make sure we are very comfortable with this. Okay. Now let's just write it down and quickly compute it. u1 equal to 1, u2 equal to 0, given u1 equal to 1, u1 equal to 2, u2 equal to 0. Okay, now I'm going to ask for your help. Please help me fill in each of these. So what is u1 equal to 0? Probability that u1 equal to 0. Yeah, it's 1 over 3. Why? Because u1 is given as uniform 0, 1, 2, right? So let me just fill in all three of these because we know all three of these are 1 over 3. Okay, somebody tell me what is probability u2 equal to 0 given u1 equal to 0. Somebody else. Half. I hear half, which is correct, right? Because it's basically this branch. Right? If you're at 0, then the next one is 0 with probability half. What is probability that u2 equal to 0 given that u1 equal to 1? Yeah, I hear 0, which is again correct. Why? Because if you are at 1, so you are here, then the probability of going to 0 is like 0, right? There is no way you go back to 0. And again, this guy is half. So after you compute all of this, you will get this thing is equal to 1 over 3. Right? So, right. Right. So its quick note is that for a Markov chain, if you can show that like u2 and u1 have same distribution, that is enough to show that it's stationary. So this implies that it's a stationary Markov chain, and you can easily check that it is stationary here because see u1 had a uniform distribution, and if you compute u2 equal to 0, u2 equal to 1, u2 equal to 2, you will again get the uniform distribution. So the distribution didn't change in one step, and then just by induction you can show that it won't change in the next step also. And then you can show that all joint distribution, nothing changes. So it's stationary chain. At every step, each of these guys have one third probability of being in that state. Right. If you don't like fully appreciate it, it's fine, but you will have questions in quiz, so just know that this can be done. This I will leave as a homework. You will have a quiz question which is very similar, which is that if you start with probability if you assume that u1 is equal to 0, actually can somebody help me? Is the process still stationary? Can somebody tell me what is the probability that u2 equal to 0? If u1 is 0, u1 is known to be 0 with probability 1. Yeah, I hear that u2 is 0 is probability half, right? Why? Because u1 you know definitely is at 0, right? So u2 will be back here with probability half. So is this process stationary? It's not, right, because clearly the probabilities change. Stationary means that the probability stays constant across time steps. Okay. So it's important that when you have a Markov chain, like you start with the correct distribution. If you don't, then it won't be stationary. Yeah, it's like, that's good to know. I think many of you have done probability, so hopefully nothing new here. Okay, this is probably the more interesting question from a compression perspective. So given this sequence, right, that we just made, can somebody suggest me a way to make it into an IID sequence? This is a Markov sequence, it has dependence, right? Can you help me make it into an IID sequence? And maybe I will write it in a way that will be like easier to understand. So you have U1, then you have U1 plus Z1, where plus is like modulo 3, so you won't write that. And then U2 plus Z2, then U3 plus Z3, ... where Zi's are IID Bernoulli half. Okay, so if I write it in this way, can somebody suggest how can I convert this into a IID sequence? This is my U1, this is my U2, U3, U4. Yeah. Yeah, very good. So you just subtract them, right? So you take like U2 minus U1, which is Z1, right? And then U3 minus U2, which is Z2, and so on. You just subtract them, again modulo 3. And when you subtract them, you get these Z1, Z2 guys, which are IID. Because by definition, the way we defined this is like this, right? So even though originally the process looked more complicated, it had dependence. If you just subtract the consecutive ones, it becomes IID. Not always true, never, like it's not always this simple, but oftentimes you will see that you can do simple transformations on your data. You start with a stationary process, maybe you start with a non-stationary process, and you just do some simple tricks, it becomes IID, and then you apply your favorite Huffman coding or ANS or whatever you like, right? And we'll see this again and again, especially in the lossy compression part. So this is like a very simple transform in a way. It's like delta coding or diff coding. Right, any questions so far? Okay, so we will just make it more general, and this will be somewhat important. We'll look at codes for this, but basically the idea is you can generalize this Markov thing, right? Where the Markov thing we said was, given the previous symbol, you don't have any dependence on the further past. Kth order Markov means that your current symbol just depends on the previous k symbols. If you know the previous k symbols, that is all you need to know. Knowing the further away past doesn't matter, right? So if you like to think in terms of like prediction, so what we are saying is un minus 1 through un minus k is enough to predict un. Like knowing things even before n minus k won't really help you in predicting un better, or like knowing the distribution better. Let me just read through the definition. So a kth order Markov source is defined by the condition probability of un given its entire past is same as the probability of un just given the last k symbols for every n. In words, the conditional probability of un given the entire past depends only on the past k symbols, or more precisely, un is independent of the past older than k symbols given the last k symbols, right? So knowing the last k symbols is the best predictor for un. So we saw that in stationary sources you could have like arbitrary time dependence, but in kth order Markov source you have just past k symbols you depend on, and then so if you are like generating this, you take the last k sequence, you generate the next one, then you take last k, generate, so on. So most practical stationary sources can be approximated well with a finite kth order model, and you can go higher k and then you get a better approximation with diminishing returns. Okay, any question on kth order Markov sources? It's a generalization of first order. Like the normal Markov source we just saw. So just to when we just say Markov, we usually mean first order. And when we say IID, we mean zeroth order, because IID is like, you just depend on nobody. So K is 0, right? You don't need to know any past to predict the future. Okay, let's quickly look at a non-example of a, I guess I told you the answer, but say you're at a bus stop, right? Which is like reasonably regular. Buses arrive at roughly 15-minute frequency. And like these are, let's say, the bus timings, 4:16, 4:28, 4:46, 5:02. Is this a stationary process? Is this sequence of times, bus arrival times, is this stationary? It is definitely random, right? Because buses have some randomness in when they exactly arrive. But is it stationary? Is it IID, first of all? Is it stationary? So what are the properties of stationary processes? Among other things, we heard that the mean doesn't change with time. So do we think the average bus arrival time keeps, like if the first bus is expected to arrive at 4 p.m., is the second bus also expected to arrive at 4 p.m.? No, right, it's expected to arrive at 4:15 and the next one is like 4:30 and so on. So this is not a stationary process, right? Like in particular, the mean increases with time. Okay, is that clear? That this is not stationary, right? Because just buses, not all buses are supposed to arrive at the exact same time. Okay, can you convert it to a stationary process by doing a simple transformation? Yep. So again, the answer is just take the difference, right? This is like surprisingly common. Like in real life data, you will see a lot of times, like we will see a lot of compressors, this lecture, next lecture, so on. All of them will work wonderfully on stationary sequences. But if you give it a non-stationary like this, they just start failing. Like you take the best, like state-of-the-art, like Z standard or one of these compressors, you give it a file which has like 1, 2, 3, 4, 5, 6, just a sequence of numbers, which is trivial to predict. Like you know the previous one, you just do +1. And it will just do a terrible job at compressing it. But if you just like do this delta coding or this difference between the consecutive ones, it just becomes a sequence of like very similar looking values, and then suddenly the compression improves, right? So again, very important to like, that's why this theory is important, right? Like you understand where do these compressors do well, where do they not do well, and when they not do well, can you convert it into a different sequence, right? So here again, you do the delta or the diff, right? You just take this difference, right? So you just do like 428 minus 416. This is like 12 minutes, right? This is like the, if you have done like process, this is like an inter-arrival time, usually modeled as a exponential distribution in theory. Right. Okay, let's move on to information theoretic quantities for non-IID random variables. If you have no questions. Right. These you will see in your homework. So I guess hopefully this will help you with the problems. So we saw the entropy, right? I hope everybody remembers entropy of U was, we did like PU log 1 over PU over all the U's, right? This was the entropy. So here we define the conditional entropy of U given V. So now we have two random variables, U and V, which are not necessarily independent. And this is defined as this thing. This is the, so you can write this as expectation of log 1 over PU, right? But So similar, very similar formula. Good. Okay, and then you can expand it out. We will try to do one example in class. So you have, this is just the definition of the expectation, nothing very clever here. Second step, we use the chain rule. So we do PUV as like PV multiplied by PU given V. And then you take this big thing and you can write it like this. So really we are defining two quantities. We are defining two quantities. So one is this thing, which is this you can like read as conditional entropy of U given V is equal to V, right? So if you know that V is equal to small v, then what is the conditional entropy of U? And this one is nothing different from what you have already read, right? This is just the entropy of, if you take this distribution, U given V equal to V. This one you have already seen. So let's say, for example, right, if V equal to V implies that U is like Bernoulli half, for example, then the entropy of U given V equal to V, somebody tell me what is the answer? What is the entropy of Bernoulli half? 1, right? So this one we are very comfortable with. We have seen this a million times, like this sort of simple thing where, not a million, but like a few times now. Okay, and then the second thing we define is this, which is the just conditional entropy of U given V. So this is an average of the above quantity. So this is like on average, what is the conditional entropy of U given V? And therefore it is defined as PV HU V equal to V sum over V. Can somebody remind me what was the intuitive meaning of entropy? Like if entropy is high, what does that mean? Yeah. Exactly, right. So entropy was a measure of uncertainty, it was a measure of randomness, right? If it's a constant, it's zero entropy, uniform maximum entropy, right? So can you guess what is the meaning of the conditional entropy of U given V equal to V, based on what we know about entropy already? So let's say knowing that V equal to V, small v, makes U deterministic, then the entropy will be very small, the conditional entropy, right? So the conditional entropy is really, again the uncertainty left in U, or uncertainty in U, given that you know something about V, right? So this thing is a measure of uncertainty in U given that V is equal to V, right? So if you know the value of V, what is the uncertainty in U, right? And this guy is the average uncertainty in U given V basically. So on average, if you know V, how much uncertainty do you have about U, right? So just to like think of an example. For example, you have like you're playing like this murder mystery type of game where you like have suspicion on a bunch of different suspects, right? So that is U. U is the variable that represents who is the murderer, okay? And then you keep getting specific clues, right? So maybe you get some fingerprint clue. And maybe that will change the uncertainty in who you think the murderer is, right? You will find that some clues will increase your uncertainty. Like earlier you thought, oh no, I think this guy is the murderer. But then you see this clue and then it confuses you again, right? So what you will see is that this quantity can be bigger than or smaller than the entropy of U. Knowing a specific piece of evidence can increase your entropy or decrease your entropy. But you will see that on average, knowing more can't hurt you. the more you know about V, it will never hurt you in terms of U. So it will decrease your uncertainty, right? So as you play this murder game, over time, as you get more and more clues, your uncertainty will keep reducing. And if you are a good detective like Sherlock Holmes, you will converge on the correct culprit. Okay. Any questions? Okay, let's try to do this example. So you are given this distribution. This is a joint distribution between U and V, right? So the way this is written is like this cell is probability that U is 0 and V is 0, right? And this cell is like U is 1, V is 1, right? So if you read this, and I would encourage you to do this carefully at home, is that you will see that U is actually uniformly distributed in 0, 1. And knowing that U is 0, so that is the first row in that table, means that V has equal probability of being 0 or being 1, right? So what is the formula we use here? It's like this guy. V equal to 0 given U equal to 0 is simply PU equal to 0, comma V equal to 0 divided by probability that U equal to 0, which is like 1/4 divided by 1/2, which is 1/2, okay? And if U is known to be 1, then you see V has no uncertainty. V is definitely 1. So if U is 1, then V is 1. Right, so this is simple stuff, okay. Can we try these? Okay, so what is the entropy in V given that U is equal to 0? So U is equal to 0. Yeah, entropy in V given that U equal to 0. It's 1, right? Why? Because we saw that if U is 0, then V is simply Bernoulli half. So that has entropy 1. What about this guy? Entropy in V if U is equal to 1. It's 0 again. Why it's 0? Because this is deterministic. Knowing U equal to 1 definitely tells you V equal to 1. And now we'll just calculate the entropy, the average of these quantities, which is PU equal to 0 times HV given U equal to 0 plus PU equal to 1 HV U equal to 1, and then you can do like half times 1 plus half times 0, because we saw that U is Bernoulli half here. So this is just half, okay. And a few things I computed at home was that the entropy of U is 1 because it's Bernoulli half. Entropy of V is 0.811. So you already see that the entropy of this guy is bigger than equal to this. So you see that knowing U has decreased your uncertainty about V, right? So knowing just V on its own had some uncertainty 0.811, but knowing U reduced it to half, right? But you see that if you know U equal to 0, that actually increased your uncertainty, right? Because knowing U equal to 1 reduces your uncertainty about V, knowing U equal to 0 increases your uncertainty about V, and then on average, it still gets lower. And this is a calculation that you can do very easily, which is like, you just take all 4 things in the table and do like this sort of thing. So half plus half, I think it will be 3/2. And you can verify that this is actually equal to this thing, HU plus HV given U. So this is the chain rule for entropies. So the joint entropy of U and V is actually equal to the entropy of U plus the entropy of V given U, right? So the overall uncertainty in U and V combined is the uncertainty in U and the uncertainty in V given U. Right. So, few properties about conditional entropy. First is that conditioning reduces entropy, which is that entropy of U given V will be less than or equal to U with equality if and if U and V are independent. So if U and V are independent, they will have the same. So knowing anything about V will tell you nothing about U. And this is the thing I was telling you earlier about, like a specific piece of evidence can increase your uncertainty, but on average, knowledge will always reduce your uncertainty. Knowing things is good on average. Okay. Let me just show all the properties at once. Okay. Then we have the chain rule of entropies, which is this. That the entropy, joint entropy is, if you remember the chain rule we saw before for IID, if you recall, not IID, just for independent, the entropy was like sum of these entropies, right? But for non-IID, in more general case, it is actually this formula, like HU plus HV given U. Let me like quickly state it in terms of compression, because that's the class we are in, right? So you remember HU was the best thing you can do for compressing U on its own. HV was the best thing you could do for compressing V on its own. And in fact, HV given U is the best thing you can do for compressing V if you know U. So this is like the minimum number of bits you can use to compress V if you knew U, right? So what we are saying is, if you want to jointly compress U and V, what you could do is you first compress U on its own, and then you compress V given that you know U, right? So it's like a two-step compression process, where first you compress just U and then you compress V given the knowledge of U. So that is, and the bits add up basically, right? So maybe this guy uses 1 bit and this guy uses like half bit. And so overall you get like 3/2 bits for jointly compressing U and V. And the last thing which you see here is saying that the joint entropy between in U and V is either equal to or smaller than the sum of the entropies, which means that if you independently compress U and V, so let's take an extreme example, right? Let's say you had a random variable which was like either 1 or 0, and then you had a second random variable which was always the opposite of the first random variable. So if the first random variable is 1, then the other guy is 0. If the first one is 0, the other is 1. So if you compress them independently, they will take 1 bit each. Whereas if you use the knowledge of the first guy to compress the other guy, then you can compress the second one for free, right? So I hope this is somewhat right. So if we do this example, simple example where if U is Bernoulli half and V is like 1 minus U, right? So HU will be 1, so will be HV, but the joint entropy of U and V is actually still 1. So this is like less than HU plus HV, right? Here, like knowing one of them basically tells you the other one. So compressing them jointly is much better than compressing them independently. So that is sort of the whole idea about this, all of this, right? There is a question in the quiz. There is a question in the homework. So do those, and I hope you will get like very comfortable with these quantities. Any questions? Okay, just in general, you can have this condition on the past n things instead of just conditioning on the past thing. Great. Any questions? Okay. Now we define like the real quantity for stationary sources, which is that what we want to do is we had entropy, right? We know entropy was the best thing you could do for compressing IID sequences. Now we want to compress stationary sequences or Markov or any of these guys. So we will define something called entropy rate, which is defined for any stationary process, right? And not only one, but two ways of defining it, right? So you like sort of buy one, get one free sort of deal. There are these two definitions. We won't go into the proofs, we won't go into very specifics, but basic idea is that entropy rate of a stationary process is defined in two ways. First way is you take you take the past n symbols, you compute, if you know the past, how much is left in the future, basically, that's what you're trying to do. So if you knew the first million symbols, what is the remaining entropy in the next symbol? How much is each next symbol adding, basically the uncertainty? That is your entropy rate, and it's defined like this. This is the limit. The second way to define it is, again, you can think in terms of compression. If I want to jointly compress n symbols at a time, and then take like the per symbol, how much am I paying for compression? And then you take the limit. So you make the blocks bigger and bigger, bigger and bigger, and you see like per symbol, how much do I need to pay for compression? So there are like two ways of defining it, and in fact, you can show that these two are equal for any stationary process, and the limit is called the entropy rate. We won't have that much use for it. Really, I think if you want to remember one of these definitions, remember this guy. This is the main one. This is the one we'll use more frequently. This is in terms of like how much extra. Let me write it down. So this is like on average bits per symbol for large blocks, right? And this one is additional entropy per symbol given the past, right? So how much each symbol, how much extra entropy is it adding to your thing? And we'll look at a couple examples in a minute. Okay, I guess we'll look at the examples. So actually what happens is, for a fair coin toss, if you look at this guy, u1 through un divided by n, if you remember from your previous lectures, this is just this. So this is just one bit. Basically, the joint entropy of the first n symbols is just n times the entropy of the first symbol, and which is one bit. So this is for IID sequences in general, the entropy rate is just equal to the entropy, right? So for IID, entropy rate is equal to entropy. The Markov thing is a bit trickier. Maybe let's just try to compute this one. So let me go through the logic. So the idea is, so if you know u1, so like you can assume, let's say u1 is equal to 0, for example, right? u2 takes two values with equal probability, right? We just saw this example in earlier in class, right? We saw that if u1 is 0, then u2 can be either 0 or it can be 1, each with half of probability, right? So therefore, it's like easy to convince yourself that actually HU2 given U1 is equal to the entropy of a Bernoulli half random variable, right? Because you take two values with equal probability, and this is just one bit. And then what you can convince yourself is that UN given UN minus 1 dot 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 U1 is actually just equal to UN given UN minus 1. And why is this? This is because of the Markov property. Markov property says that if you know the last symbol, the previous symbols have got nothing to do with the next symbol, right? Just the last symbol is the one you care about. And so that's it. Basically, you get the entropy rate as one bit. Let me pause here for a second. There is a quiz question very similar. I think feel free to compute these carefully. Let me just write it clearly. So for IID, there is a entropy rate written in different ways depending on the text. I will just try to use a boldface italics type U, is equal to the HU1 basically. For IID, the entropy rate is just the entropy of each symbol. For kth order Markov in general, the entropy rate is the entropy of the k plus 1th symbol given the first k symbols, right? So in these cases, the entropy rate is easy to compute. And basically the idea is that if you know the past k symbols, how much uncertainty is in the next symbol. That's the whole idea here. Let's look at a real example. English. So you can take a lot of English text like a big corpus, and then what you can try to do is try to estimate the probabilities, like you estimate the probability distribution, right? You make a probability model out of English. You take 2 symbols at a time, you take 3 symbols at a time, three characters at a time, 4 characters at a time, so on, and you make this probability table. So what you could do is you could find probability of u, or you can find probability of u1 comma u2, like 2 characters at a time, or you do like u1 u2 u3 and so on. So you can make more and more complicated models of English. You can just so for example, how would you estimate this? So if you do what is the probability that u1 is a and u2 is c, so this will be number of times you have seen some xn equal to a and xn plus 1 equal to c divided by total sort of thing, right? So you just empirically estimate, right? If you have seen this AC combination 1,000,000 times out of 1,000,000,000 times, then you do million by billion sort of thing. So somebody did this for some English corpus, and what they found was if you assume it's IID, so 0th order Markov chain, they got 4.76 bits per letter. So this is what they got. And as you might imagine, as you take more and more history, your uncertainty will reduce more and more, right? Because you can use that to predict the next symbol. So if you take a first order Markov chain, so if you use the previous symbol to predict the next symbol, so now suddenly you can use the fact that after a Q, you mostly get a U sort of thing. And suddenly you do slightly better. You do 4.76 to 4.03, right? So your entropy rate or the conditional entropy reduces, okay? Maybe you take four previous characters. For example, if you see THI, then you know it's a this or it's a thing, so N. So you are even more certain about your prediction, and the entropy reduces further. It becomes 2.8. And then Shannon in 1952 actually did a very interesting experiment where he got a few people, I think his wife actually, but he got some test subjects basically, and they gave him up to some symbols in some English text and asked them to predict the next symbol. And then they predicted the next symbol, and they say what is the probability of, did they predict the right one or not? And then you predict the next symbol. They got a human to actually predict each symbol, and they used that to estimate the entropy in English, how much uncertainty is in English, assuming that a human is a perfect predictor. And they got 1.3, right? You see a fourth, it's much better than a 4th order model, and which is true, right? The previous word tells you a lot about the next word. The previous sentence tells you a lot about the next sentence. So the dependence is goes a bit farther than just 4 characters. And obviously now LLMs have beaten humans. So yeah, if you look at the latest models, we'll look at them in the next lecture. They get a rate which is even lower than this. So they have become even stronger predictors of English than humans at this point. Subject to the experiment being done in a specific way. Anyway, okay. So last slide for today. Just in the previous one you saw it, we said bits per letter, and I've been using compression analogies all the time. So basically, kth order Markov source. The best compression you can do is basically this, the HUK given UK minus 1 ... U1. And in general, for a stationary source, entropy rate is the best compression you can hope to achieve. This is the takeaway. So just like the AEP property or typical sets that you read about in lecture 5, there is a similar property called Shannon-Macmillan-Bremen theorem, which says that the probabilities of these blocks are roughly equal to the 2 power minus entropy rate. So it's exactly the same property you saw before, just replace entropy by entropy rate. You need some technical conditions which we won't go into, but basically that's why these quantities are important, because again they give us the best you can do in terms of compression, right? If you have a first order Markov source, then HU2 given U1 is the best compression you can get. And if you have a general stationary source, the best compression you can get is the entropy rate. So next lecture, what we are going to look at is, we will actually see how we can achieve this entropy, this conditional entropy. How do we work with these dependent sources? And we will look more into, first we'll start simple, just first order. Then we'll go to like kth order. And then we'll just say any stationary source. So just rapidly increase the generality of our ideas. And we will use arithmetic coding, as you might have guessed. Okay. Thank you. Happy to answer any questions.